Hello, it's James here. Yes, it's another robot project. In the video a couple of weeks ago, I gave away all the CAD and code for Robot X, which is a robot that can just walk along, and I've published those as open source. And it's a truly open source project, which means you can sell it or distribute it or change it and redistribute it or sell it, as long as you publish any changes to the source. So we're going to continue on that trend with a project called openDog, which is going to be based on the Boston Dynamics dog robots. Obviously it's not going to be quite as good as that because I'm not as good as Boston Dynamics, but this time we're going to do the project in a slightly different way. I actually planned the project first, instead of building it as I go, which is what I normally do. With Robot X I built the mechanics and I tried to work out how to control it. This time we're going to do an actual mathematical model based on the CAD, do all of the planning, write some of the code, then actually build the mechanics. And it's open source as well, so I'm in fact going to be publishing source, the CAD and the code, in every episode as I make them, including this one, and you can find the CAD and code for this episode in the link in the description below. Now I don't recommend you build along, because probably I still need to sort out some issues as I go, the CAD will get more detailed as we go, and so on, but it is a truly open source project, and those links are there just to prove that. So I've already planned this quite well and done a couple of revisions of the CAD, so this is my first model that I started with. We've essentially got a knee joint here. We've got no foot joint because we're just going to have some sort of spongy, grippy foot. Haven't really decided yet. And of course we've got another joint at the hip here. And we've got another joint that allows the legs to be lent in that way. So we've got 3 joints per leg, 3 degrees of freedom essentially. And that means we've got 12 motors in the whole robot. And you'll notice in this initial planning phase, I've got these pivots at the top. They're in line with the main sticks that make the legs. And that seemed pretty logical. But trying to work out a mathematical model for that's a bit harder. So what I've actually done is come onto this version, and you'll notice what I've done here is actually moved these pivots so they're off centre from the main supports of the leg, and in fact they're in line with these ball screws. And what we're going to do is actually have ball screw actuators like the exosuit that move those joints, and so you can see that slider there. We've made that actual motion link and everything in Fusion 360 that makes that leg work. I've also done the same with the upper leg there, so you'll notice again that pivot for the shoulder, or the top of the hip if you like, is in line again with that ball screw, and again we can see that joint in motion. Haven't quite decided how the other one's going to look, but it'll be another ball screw pushing that stick and basically pushing those legs in and out, and those ball screws will lie in between the mechanisms there for each hip. So most of this is going to be made out of aluminium extrusion, and we'll look at the parts shortly. It's going to be quite big. This main rod here is 900mm long and it's going to stand about 600mm tall. I'm estimating the weight to be about 30 kilograms, so altogether it's about the size of the Boston Dynamics Spot Mini. So there's going to be 3D printing in it. There's also going to be some metal parts which I'm going to make on my new CNC machine. So have a look at those episodes as well. So here's that main beam in real life. It's a piece of 2080 C-section aluminium extrusion. It's pretty hefty, and there's some more of this as well, or at least smaller pieces for the legs and so on. I was a bit worried the weight was going to add up, but actually the weight of the ball screws and all the motors will overwhelm this incredibly, so I'm actually not too worried. Obviously it's extrusion, so it's relatively light. So we've got that main beam for the back there, we've got a piece of steel tube, and that's going to be used for the leg pivots. We've got some 4040s, and these are actually going to be those pieces which the hips are pivoted on. So those are going to have some aluminium plates CNC'd on either side, so that'll actually be the hip pivot. We've got all of these for the rest of the legs, so we've got some 6020 and some 2020s. So all these long boxes are the ball screws, and we've got different lengths. Those are for the side-to-side hip movement, and then we've got the 250mm which are going to be for each joint on the leg. So I've still got some more ball screws to arrive, and these are the sets that come with the mounts that go on each end, and the coupler which I probably don't need, and this is really similar to what I did with the exosuit. And these are the motors. So we've got a load of the Turning G Aero drive, 149 kV, 63mm diameter, 74mm long, outrunners there. So these will run up to 2 kilowatts each at about 50 volts. I'm going to be running them at 24, so they'll only peak at 1 kilowatt. This is basically the same motor I used in the exosuit, only we've got 12 of them this time. And in the same way we did the exosuits, we're going to be driving that motor straight onto the ball screw shaft with about a 3-to-1 reduction with T5 pulleys. I'll probably 3D print them to start with, eventually I'll probably upgrade to metal ones. And that gives us quite a good reduction, and of course most of the reduction is actually happening on that ball screw, which gives us zero backlash. So I had actually considered replacing these with planetary gearboxes just on the end of the motor, turning the joint. I had a good planetary gearbox that would probably have fitted this motor that I used in the BB9E project, but actually it's really heavy and there is backlash, so there's gaps in between the gears, and you don't get that with a ball screw. This has practically no slack in it at all, so this makes the joints much tighter and more accurate, and I think these are actually lighter than the planetary gearboxes. So in order to position the joints on the exosuit, what I did of course was tied a string around the joint, and then that moved a pulley which had a potentiometer attached to it, and that's how I got the position feedback on those joints, so I could position them and basically make sure they didn't run their end stops and so on and so on. That wasn't very accurate though, so what I'm actually going to do with the dog project is in fact go and measure the position of that ball screw moving up and down. And that's pretty easy to do because obviously we've got the motor turning, so we can put an encoder on the motor, we can put a home switch at one end of the ball screw to home it, and then we can work out a quite high resolution using an encoder how many times the motor's turned, or where it is in one revolution even, and that should give us quite accurate positioning over the length of the ball screw. And then using trigonometry, of course, we can work out the angle because it's a triangle, and we know what the sides are, and therefore we can work out basically what the angle is at the joint. And that's why I've offset the joint here, because it makes it much easier if that's just one triangle between these pieces rather than having the joint offset at the bottom of this. So obviously it's really important we can accurately control that motor position and therefore the ball screw position using an encoder on the motor. So what I've got on the table is an O-Drive Robotics dual motor driver and an Arduino and a motor and an encoder. We're going to give that a little demo. So this is a dual motor driver. I've only got one motor connected at the moment. We'll in fact drive two motors at once with encoder feedback, and that makes some really good value. There's a number of ways of driving it, including USB and UART serial, and there'll be more interfaces supported in the future, such as CAN bus, although it's not in the firmware at the moment. Now this is a 3.3 version board, 3.5 is out, and the firmware is getting updated all the time, so it will eventually support more things like daisy chaining them together on CAN bus and so on. Now I'm using one of the motors here for testing. I've got the encoder fitted, and this is an encoder with a Z index, and that means that I don't have to calibrate the encoder on every power up. Now you can buy these encoders from the O-Drive website, and we'll have a look in a minute at all of the setup instructions. But for now we're just going to do a little demo with the Arduino library. Okay, so here's my Arduino example. We've got, we're actually using software serial, and we've got the O-Drive library brought in there. So we're using software serial on pins 8 and 9 on the Arduino. Obviously I'm using the only other serial interface to communicate with a terminal. So there's not much choice here, although it would be better to use two UARTs if we had them on a Mega or something like that. So basically we've got a bunch of parameters here that are set. Now I will say as well that I haven't really tuned up the motor. There's a lot of stuff in firmware where you can set the maximum speed, the maximum current, the holding current, and a lot of things like that. And I haven't set those, so it's set at the default, which is pretty low. I think it's only 10 amps, and there's a maximum speed set. And all of these parameters are tunable though, both in firmware, and these ones can be changed on the fly, so like the velocity can be changed on the fly in the code. So this is the example code, but I've actually added a bunch more characters here to do various things, and those are all called down here. So for instance, to get the encoder position, we can do a poll of the position there. To get the bus voltage, there's various functions that are fairly well documented in the Arduino library. So if we bring up a terminal here, we can actually get it to do some stuff. So if I press S, for instance, it should go and do its sinusoidal move, which speeds up and slows down. We can see quite accurate control there on a sine wave, and the example actually controls both motors but only have one connected, of course. I can read the motor position, but first of all I'm just going to turn the motor, and then we'll read the position, and we can see that now the position is 10,000. I think I'd set it to move 10,000 encoder clicks, and it's just overshot slightly, but I haven't tuned the PID controllers up, which is actually handled in the O-Drive, and that's part of the firmware. So I can move that back again, and I can also turn up the speed, and I've just got a thing that turns it up to twice the value, so now that motor moves twice as fast. We can also just make it run at a particular velocity, so if I just press E, off it goes, and if I press D or C or whichever one, oh yeah, I can change the speed there, or I can stop it completely, and again we can read the position there. That gives us a much bigger encoder value, and in fact A and B do the test 1 and 2 are setting a particular position. So if I press A, it should go all the way back to where it started. And now if we read the encoder position, Yeah, we're about to 10,000 again, so I think position B must have been 0. There we go, only overshot by 1, or undershot. So that does everything that I really need to do. I should also point out that it does have holding torque as well, so with the motor just idle there, if I try and turn that, it will actually resist me, and it will try and turn back to where it was. Obviously it's only got 10 amps holding it at the moment, so it's not too hard to turn, but I could go up to 70 amps. So that would hold its position pretty well, and obviously geared down with the ball screws, that's going to do fine. So this is the oDrive website. The documentation is very good. There are some more videos and some examples of this in motion. So we just come down to this video. You can see that basically that is obviously going much faster than my motors, which is great. So drawing a circle there. So this is an XY chassis with 2 brushless motors, probably very similar ones, controlled by an oDrive. So that seems to work pretty well. You can find all the instructions, in fact, on the GitHub. I'll put the links in the description. The instructions, as I say, are complete and accurate, and I've managed to do everything to make this work. You do need to look at these 3 links for downloading, building the firmware, flashing the firmware, and configuring the board, and that's important to actually make it work. The Arduino library is a separate repository, and again I'll put that link in the description. So although there are details which will get worked out through the build, the nitty-gritty detail of how the joints and the bearings and those things hang together, the main thing I need to be really careful of is that I can actually work out the mathematical model, and that's what needs planning. So we need to talk about a kinematic model and an inverse kinematic model, and I'm going to demonstrate that with this robot arm I made for another project. I made this robot arm for the start of the Ultron series, so check that out. It was a while ago, but it's quite useful for the demo. So we've got an arm here with some servos. It can rotate this way, and it's, let's just see, its arm can move that way, and the end can rotate here as well. So basically, if we were going to work out a mathematical model for this, it shouldn't be too hard to say, well, if we position this joint to a particular position, let's just say sort of there, and we position this one, and we rotate this, then we know the lengths and we know the angles of all the joints, so we can work out where this end point is, and typically that would be in an XYZ grid, so Cartesian coordinates. Say this table is square as it is, and X, say, runs that way, Y runs that way, and Z runs up. We could work out where that end position is just by working out the maths of the joints and the lengths of the robot arm, and that'll be easy enough. But actually what we practically probably need is the ability to say we want to put that end point somewhere, say over here, and then what do we need to do to work out all of the joint positions to get that there? And that is the inverse kinematic model, and that's quite important. And it's quite important that we build the robot so that's easy to solve, because working back the joints is a little bit harder. And if we have weird offsets like we have here, where this piece rotates on the middle, but then this joint is offset, that requires extra maths to work out to take into account that offset. It would be far better if the joint was right on the same pivot point. And that's why I've designed those robot leg actuators and the push rods to be in perfect triangles. So this is easier to explain if I pretend to be a dog. So basically, if I want to move my front leg forward in a straight line, obviously my arm has to extend and this elbow has to extend, and it bends back again when I put it back in place there. So it would extend again that way. Similarly, if I wanted to move it in a straight line sideways, my arm or leg would have to get longer there to stay in a straight line. And if I move it up and I move in a straight line, then not so much. So what I really need to do is change all of those joints that move this way into basically the ability to move in a straight line in each direction. So it's very important that as I track this position in whichever direction, that I can work that mathematical model back and tell each joint what angle to go to. So most of that stuff can be worked out using trigonometry and various other mathematical processes, but it's very important that I make sure that that can be worked out and there aren't too many unknowns in the mechanical mechanism. So I've started thinking about this already, of course, in the design, and I've also started to make this controller that I can actually control my dog with in code, get the numbers out of the code, put that back into the CAD, measure the distances, and check that in fact I can write code that will work out that inverse kinematic model. So here's the controller that I've built. I was going to use the one for Robot X, which was supposed to be a universal robot controller, but it doesn't have enough joysticks on. So at the moment, this has got a little display. It pairs with Bluetooth. There's an Arduino inside it. I've got another Arduino with the other Bluetooth module, which I'll be using for testing initially. It's all made of Mega 2650s, they might need upgrading to something more powerful, but for now it's fine for testing the code. So the other features on this joystick are menu buttons with an execute button, and also these two joysticks. Now these are like normal joysticks that move in both directions, but also the tops rotate. So that gives me 6 axes. So let's just assume this giant Lego man is my robot dog for now. So my 6 axes will be transitioning in a straight line this way, and of course making the legs longer and shorter to transition this way, keeping everything on those Cartesian coordinates. Once I've been able to work that out, then I'll be able to rotate the robot and also pan and tilt it. So those are my 6 axes, and that's why I need those 2 3-axis joysticks. Now of course it'll be able to do that by keeping its feet still on the ground, which essentially means I'm going to calculate the foot position and keep those in sync. And once I can do that and I can move them in X, Y and Z, then I can actually plan the gaits, the style of walking, by moving those feet to specific positions in that XYZ coordinate space. So my first challenge, the first bit of maths we need to do is work out the leg length, and that's from the top pivot there to the foot there. So basically that makes a sort of big triangle there with that joint right there. So the thing I want to do is put in the leg length, and what I want to get out is that actuator distance. So we need to divide this into triangles to work everything out, and the first one's actually going to be a right angle triangle here. So I can work out this angle, then I can take that away from this angle, and then when I've got that angle, I can then use this triangle with that angle to work out the actuator length, which will be there. And that's the distance I need to drive that actuator to. Of course, as I move the elbow or the knee, whichever way you look at it, that actually brings the end point of the leg forward, so we'd have to compensate with that joint there. But what I've cleverly done is made the leg length between those pivots and where the foot will eventually be. Then in fact I can just move the top joint half the distance of the bottom joint, and that will keep the leg in a perfectly straight line. So once I can drive the leg length and I know how to control those angles and control those actuator lengths, the rest is pretty easy. So the rest to move the foot in a straight line this way is just a triangle here like this, and if I want to move it to this point, it's just a triangle like this, and that tells me the new leg length, and pretty much that's it, the leg length and the angle up here. So that should be very easy to make that foot then drive in straight lines, and the same with the sideways axes as well. And that's all thanks to basically offsetting this ball screw here, so that this makes a perfect triangle and there's no weird offset with the joint over here, which would be much harder to solve. So let's have a look at some code. I've got my Bluetooth transmitter there paired with the other Arduino that's running the code, so the transmitter is literally just sending all of these positions. I'm only using one stick at the moment, which is the rotation there, and the other Arduino is getting the data and doing the calculations. That'll eventually be the dog's brain or something more powerful. So I'm receiving all of that. I'm using Easy Transfer by Bill Porter as usual. So I'm basically receiving this data set, which is all of those remote buttons and the 6 axes. I'm going to publish this code anyway. I'm not going to talk about it in too much detail. Essentially it's multitasking using millis and checking times. There's various stuff here for driving the remote, so the actual display on the remote eventually will be slaved back to whatever mode the robot is in, so it'll send the key presses and the robot will send back its mode, and that'll tell the remote what mode it's in, rather than that being controlled by the remote and trying to keep the robot in sync. So this is the nitty-gritty of it though, for actually working out that leg length. Now it's fairly nasty code, and that's because halfway through I convert degrees to radians and back again, and that's so I can measure halfway through here in degrees in Fusion 360, which works in degrees, but Arduino wants to work in radians, which is another way of measuring angles. So really I should be using radians all the way through. I know this, but for the sake of being able to troubleshoot my code, I did that conversion, did some stuff in degrees and converted it back again. But it should be accurate anyway. And eventually I'm doing a serial print. So all we're doing so far is driving the knob to drive the leg length, and that's telling us then what the knee actuator should be. So I've got those numbers sort of just there in this serial terminal. So if we have a look back in Fusion, of course the leg length, as I mentioned, is that down to the foot, and the actuator is from here to this pivot point on the actuator there. So let's just set that actuator to something. So let's just put that like that. And then we're going to measure the actuator there. And that says 114. So let's go back to this and just turn that knob till we get 114. That's the wrong way. So that should mean the leg should be 607 mil, it looked like. So now we can just measure the leg. So we measure from this pivot and 605, so not far off. In fact, there should be a ball on the foot. I'm just measuring to the corner, so I probably should be measuring to the middle of that, where the pivot point will eventually be for the foot. So it's a couple of mil out, but that's pretty much right. And if we move the actuator up the other way, in fact, what we're actually going to do is demand the leg length, so it doesn't matter which way around we measure it. So a leg length 447, so let's just go and adjust this till we get 447 on the left. About there somewhere, so that should mean the actuator's 188 long from the joint. So if we were then to go and measure that again from here to the centre pivot on the actuator, yep, 187.997, so it looks like that maths is working out pretty well. And of course we can check everything in the CAD once we've written the code to make sure that's correct before we actually go and cut metal and build it. And in fact I have checked, at least on paper, that I can work back that mathematical model for the whole dog looking at the CAD I've got now, so that's pretty good. And that means next time we need to do some actual physical prototyping. So we're going to look at where those joints are floating in the air, make some 3D printed prototype parts, decide if those are strong enough or they need to be made in metal, hopefully at least get one leg joint moving with the O drive, seeing how agile it is, calibrating the encoder revolutions for the ball screw length, and checking all that trigonometry works in real life. So for now I've actually published that dog model. You can find it in the link in the description below. It's on GitHub. I've published a solid model, which is a step file, and that means you can load it into any CAD and you can actually modify it very easily, unlike an STL. I've published the Arduino code for the remote and for the dog itself. I've got so far just that little bit of inverse kinematic model with the trigonometry, and also for the remote here if you wanted to build one. And these joysticks I got off eBay, they're about £10 each and they're pretty common items to find. Obviously it's an I2C LCD using the I2C LCD library, and an Arduino and the HE05 Bluetooth modules which make a transparent serial link. So I hope you've enjoyed this. Don't forget to subscribe for more updates on the project and all the other projects. It's also really important to say that all these projects that I do are funded through Patreon. So have a look at patreon.com/xrobots, and essentially you can get access to some exclusive rewards, including a live stream with me, all the videos early, and various other things. Alright, that's all for now.